All right, well, it's my great pleasure to introduce Hokeun Kim, who is going to talk to you about his Ph.D. research, which he got a Best Paper Award for just last week. So, Hokeun, and he's been getting papers accepted right and left everywhere with really good, nice reviews. So he's firing on all cylinders, so hopefully you'll pick something up from this. And take it away.
Thank you, Edward. So thank you very much for coming to my talk. This is my dissertation talk, and it will be about security of the IoT. And the topic is a toolkit for authentication and authorization for the Internet of Things. My talk is organized as follows. I'll start with the introduction to the IoT and security, followed by the motivation and backgrounds, which will be mostly about the challenges. Then I'll present my dissertation work, SST, Secure Swarm Toolkit, and this is an open source toolkit for building authorization infrastructure for the IoT. After that, I'll demonstrate the evaluation of SST through analysis and experiments. I'll also discuss our recent ongoing effort on defense against denial of service attacks using SST, and then conclude with future work and acknowledgements. Let me begin with what the IoT is. The Internet of Things refers to all kinds of computer systems that are connected to the Internet, interacting with humans and physical world. The IoT includes the smart homes and buildings, control systems for infrastructure such as transportation and electric power grid, and environmental monitoring, for example, the air quality and forest fire monitoring. And other applications of the IoT are the factory floors used in manufacturing and healthcare and medical applications. So with sensors, actuators, controls, mobile devices, cloud computing, the IoT brings about benefits from its connectivity. However, the connectivity might not always be a good thing. About half a year ago, a company called Dyn suffered a cyber attack in which most of its servers in North America and some of the servers in Europe were seriously affected. Dyn was a provider of domain name services for translating the domain names into network addresses. Thus, this attack led to internet connection problems to major websites such as Twitter, Netflix, Spotify, and the Financial Times. This was a traditional distributed denial of service attack where a number of compromised computers forming a botnet sent a flood of network traffic to the Dyn servers to exhaust the server's resources, causing denial of service. What made this incident remarkable was the fact that the large portion of the botnet included printers, IP cameras, home gateways, and baby monitors, the Internet of Things. And those Internet of Things were compromised by malware called Mirai. The indication of this instance was that the things in the IoT were easy targets compared to the other computers in the Internet, yet powerful to launch a DDoS attack. Another incident showing that the risk of connectivity of the IoT was a cyber attack on the Ukrainian power grid that occurred in December of 2015. The hackers took down the controller of the Ukrainian power grid and caused a power outage for several hours in a wide region in Ukraine populated by 1.4 million people. The indication here was that the consequences of a cyber attack to the IoT can be life-threatening, far more than information theft or inconvenience. For example, if you think about a power outage in hospitals. As you have seen, securing the IoT is very critical and important. So let us see how we are doing with the IoT security now. Many currently used security solutions for the IoT are based on existing security solutions for the traditional internet. One example of this is Amazon's AWS IoT. This uses Amazon's famous cloud computing service, the Amazon Web Services, as authorization and authentication servers. However, is this really a right way to make the IoT secure? Well, maybe not. Let us take a look at this incident of Google's OnHub routers. OnHub is Google's smart router that can provide on internet access and control for home devices connected to it, including lights, thermostats, and cameras, the Internet of Things. A couple of months ago, a number of these smart routers and their connected IoT devices suddenly stopped it working for 45 minutes due to the failure in Google authentication servers. This was mainly because Google used cloud servers and Google accounts for authenticating the users of the Google Home on-hub routers, similarly as in the Amazon's AWS IoT. So this incident shows that we may face unexpected challenges if we just try to adapt existing internet security solutions to the emerging networks such as the Internet of Things. Okay, that was the introduction, and now I'm moving on to motivation and background of my work. So as you have seen so far, making the IoT secure is important but can be challenging. One of the reasons of these challenges comes from the heterogeneity. The subsystems of the IoT have different security requirements and resource availability. For example, the nuclear power plant will require very strong security guarantees, while it is more important to save energy for wireless sensor nodes. In addition, there can be heterogeneity in connectivity between the devices using wired connections and mobile devices. And of course, the ways of managing each subsystem must be very different. Many IoT systems operate in open or even hostile environments, and this also makes it challenging to make the IoT secure. Unlike the servers in data centers now, it would be possible for potential adversaries to physically or wirelessly access the IoT devices. The attackers may leverage this access to compromise IoT devices. One type of an attack that leverages physical access is side channel attacks, such as a cold boot attack shown here. In this example, the attacker froze the DRAM of a computer by pouring liquid nitrogen while it was still running and extracted out the encryption key by looking for high entropy in the data. And this is another example leveraging wireless access to the traffic controller on streets of Ann Arbor, Michigan. In the attack demonstration, they could make the traffic lights green indefinitely. So, in summary, operation in open environments puts the IoT at a higher risk of being compromised or captured. Thus, there must be mechanisms to revoke access of compromised devices. Another important challenge for the IoT security is scalability. The IoT security solutions must be scalable with the increasing number of connected devices and increasing data traffic, as it is expected that there will be 28 billion connected devices and more than 15 zettabytes of data traffic in a few years. All right, now looking into how we are doing the IoT security again, many of the proposed IoT platforms use TLS or its datagram variant DTLS for security, especially for authentication and authorization. And such platforms include the aforementioned Amazon's AWS IoT, OpenIoT, and OSCAR. TLS, the transport layer security, is also an underlying security protocol for HTTPS, which you have probably seen in web browsers. And TLS has been widely used and very successful for the internet, especially for web servers. TLS uses digital certificate for authentication of the web server and establishing a secure channel between the server and browser using public key cryptography. This digital certificate is issued by a third party trusted by both the server and browser called Certificate Authority. So how about we just use TLS for the entire IoT? It may work for some parts of the IoT, but we will face the following challenges. For the devices using batteries, it can be prohibitive to perform power-hungry public key cryptography and manage large certificates. And issuing and managing tens of billions of certificates will not be scalable. Also, revocation of a certificate can be problematic because the certificate authority is not involved in the authentication process once the certificate is issued. And it is hard to support one-to-many communication because TLS is based on one-to-one communication, which is a server-client model. It will be also challenging to apply other widely used security solutions to the entire IoT. Kerberos authentication system uses a temporary access token called a Toolkit issued by an authentication server. So Kerberos system can have advantages for access revocation compared to TLS. However, Kerberos requires stable connection with the authentication server, so it makes it challenging for mobile devices to use Kerberos. And it also has a centralized architecture, so there will be scalability issues. You may want to use other security solutions for the things such as wireless sensor networks and mobile ad hoc networks or swarm devices. However, these approaches assume relatively homogeneous environments, and most of them are not simply designed for an internet scale. So far I went through the motivation and background. Now I'd like to introduce my thesis work, SST Secure and Swarm Toolkit, and how SST can address the IoT security challenges. SST is an open source toolkit for locally centralized, globally distributed authentication and authorization of the IoT available on GitHub repository. This work was also presented in a Cyber Physical Systems Week conference last week. So what does this underlined phrase mean? The locally centralized, globally distributed authentication and authorization. To explain this phrase, let me begin with authorization, which is very critical for the computer security. So authorization is about controlling access to resources, including private data and control. One example is determining whether someone can enter the department building after hours. And in computer systems, allowing or denying access to resources include the rights to read, write, or execute. Sometimes you may want to revoke access. For example, when you lose your ID card, then its access should be revoked. Authentication is a process of identification, for instance, whether someone is a member of the department. This is essential for access control because it is almost impossible to grant access to someone or something without knowing its identity. Authentication is intrinsically based on trusts. The notion of trust in computer systems is analogous to the trust in the real world. Let us take this example where a police officer tries to identify someone with a driver's license issued by the state of California. If the driver's license is valid and the picture on the driver's license matches the person, then the police officer will be able to authenticate the identity of the person as stated in the driver's license. However, so this is possible because the police officer trusts the California government and its process of issuing the license. However, this may not happen for a person only with a student ID because the police officer wouldn't think the process of issuing a student ID is robust enough. And the similar things happen in computer systems. The use-trust relationship builds upon existing trust with something else, and we call the very initial trust a root of trust. So how can we set up this initial trust? There are roughly two ways of building initial trust in computer systems. One is in a centralized way, and the other is in a distributed way. In the centralized way, we ask a centralized authority like the state government in the previous example for authentication. Such systems include the certificate authority in TLS and also the Kerberos authentications. So, it's not working.
You have to
Oh yeah, right. So, thanks to the centralized control, it is easy to manage the trust in centralized systems, even though the overhead of trust management tends to be focused on the central authority, and the central authority can become a single point of failure. In the distributed way of building trust, we ask for our fellows. It is like you ask your friends whether they know someone. Such systems include many of the security solutions used for wireless networks, wireless sensor networks, OpenPGP, and Bitcoin. The systems based on the distributed trust has no single point of failure, thus they are more resilient. But the overhead of individual entities tends to be higher, and they are also vulnerable to collusion attacks, where a subset of the participants collude to deceive other entities. So both ways of establishing trust have pros and cons. In my thesis work, we adapt these trust relationships to the emerging IoT network to address the challenges in the IoT security. So going back to the phrase I mentioned before, the locally centralized and globally distributed authentication and authorization, this is how our proposed approach SST's architecture looks like. The trust is centralized in local subsystems, while the trust is globally distributed in the internet scale. The yellow circles are main components of SST. Auth is a local authentication and authorization entity, and the authorization service provided by Auth can be managed by local domain experts to better serve the heterogeneity in the IoT, including possible access revocation. Auth is a software written in Java to be deployed on edge computing devices such as Intel's IoT gateways or the TerraSwarm swarm boxes. The edge computing devices used for Auth are computers that can act as internet gateways with enough resources for access control. Using these Auth, we have been working on concrete applications. These applications include work with auto parts maker Denso, and also the TerraSwarm Research Center, a government and industry-funded project. So having such architecture was one of the specific goals of SST to accomplish the ultimate goal of addressing heterogeneity, open environment, and scalability. In addition, to address the heterogeneity in the IoT, we integrated existing security solutions rather than inventing new cryptography or protocols. Finally, we also aimed for a solution that can be easily deployed by local domain specialists at a large scale. So, for ease of deployment, SST provides an API for programming IoT applications to use Auth and other IoT services, which we call secure communication accessors. These are software building blocks in actor-oriented programming model to securely access Auth and other IoT services, and accessors can encapsulate the cryptographic keys and operations, thus help IoT application developers who are not security experts without having to worry about the cryptographic key management. Currently, we have 4 available accessors for programming server, client, publisher, and subscribers, and we used JavaScript as a language for describing these accessors. We are proposing these accessors as a starting point of ease of deployment and usability, and we are also still working to deliver more accessors. And for more information, please see the accessors website. Okay, now I'm going to explain how we can initialize SST using this example. Let's say I'm a system administrator with my own computer, and there's an Auth running on an edge device such as Smart Gateway with its own cryptographic key and database tables. And I recently bought a new camera and want to add it to the SST authorization infrastructure assuming that the camera also comes with a cryptographic key in it. Now I connect the camera to my computer and also open a secure shell client with auth to set up a secure channel between the auth and the new camera. And using this secure channel, I let these two devices exchange their credentials, the cryptographic keys, like this. And together with the credential, I also enter the new camera's basic information and its access policy. For example, who can see the images taken by the new camera. Later, auth uses the exchange's credentials to securely distribute the session keys to the camera, which I will explain in the next slide. So this example shows how SST authorization process works with auth and accessors. There are two IoT entities, the client and IoT service in this example. And both the client and the service are registered with auth a priori. And the client and IoT server are programmed using accessors where each box is an actor in actor-based programming model. When the client entity wants to use the IoT service, the camera, first it needs to receive a session key that I mentioned in the previous slide from auth. This session key is encrypted with another key between auth and client, which we call a distribution key that can be derived from the pre-exchanged credentials during the registration in the previous slide. This session key will be used for accessing the IoT service. So the client initiates the challenge response with the IoT server to check whether the server has the same session key. Then the IoT server also requests the same session key to auth using the unique identifier of the session key. And auth checks if the client can access this service and then delivers an encrypted session key to the server. So now both the client and server have the same session key. So they finish the challenge response and start secure communication protected by the session key and standard cryptography. All right, so I'd like to discuss how SST addresses the challenges of heterogeneity, open environment, and scalability. Let me begin with heterogeneity. SST provides a range of configuration alternatives for heterogeneous IoT entities with regard to the security. Each setup alternatives is like a knob that you can turn to choose between less energy overhead and more security guarantees. I will revisit this figure later to explain in more detail and show the effect of these knobs through experiments. And to limit the damage from compromised entities in the open environment, SST is designed to timely revoke the keys. In SST, all access must be authorized by auth, thus revocation takes effect immediately. For example, even a client with a valid session key gets compromised, auth still can prevent its access to the IoT service by refusing to give out the session key to the server. And for scalability in terms of the data traffic, SST provides shared key support for one-to-many communication, as shown in this example. Let us assume that there is a sender with multiple receivers registered with an auth. And auth delivers the same session key to the sender and receivers. Then the sender can efficiently send a secure message to receivers either using the publish-subscribe protocol such as MQTT or over UDP broadcast if they are in the same local network. So in this case, the security guarantees are applied to this stream of data rather than a channel. So this can be viewed as an object or data security that can help the security of information-centric networks. Auth has a globally distributed architecture to cope with the increasing number of IoT devices. And there exist peer-to-peer trust relationships among auth without a centralized authority. When the entities are registered with different auth, for example, the client here and the IoT service over there, then these two auth can collaborate to authorize their entities' access. All right. So far I talked about the SST, and now I'd like to discuss SST's evaluation through analysis and experiments. So the first evaluation is security analysis to see whether SST provides desired security properties. In SST's process, authorization process, we want to have confidentiality, message authenticity, and data integrity even under a threat of attackers. The threat model includes network attackers who eavesdrop or inject packets, and also compromise IoT entities who try to break security of others. We did not include compromised auth, assuming that auth are much better protected than IoT devices. And with this, we built our formal security model of SST using a model checking tool called Alloy. And this includes models for auth entities and communication messages. As a result of analysis, we found that SST is formally proven to satisfy the desired security properties under the threat model. And our security model and results are also available on our GitHub repository. And to discuss the scalability of SST, let me consider the authorization tasks of an auth. These tasks include the communication with IoT entities and other trusted auth, cryptographic operations, and accessing its own databases. Intuitively, if we have more IoT entities and more access activity per entity, this will lead to more authorization workload for an auth. So when the number of entities increases too much, then the authorization service may be disrupted. However, thanks to the SST's globally distributed architecture, we can distribute the authorization workload throughout multiple auth. And this keeps the workload manageable for each auth. To show this rigorously, we have shown that each auth workload is a linear function of the number of entities per auth rather than the total number of entities in the entire system, assuming that the access activity per entity is constant. Thus, in theory, we can always scale with the increasing number of entities by putting more auth accordingly. Okay, so in addition to those two analyses, we also carried out experiments to see the effect of various security configurations provided by SST. We estimated energy consumption for initializing secure connections between the IoT clients and IoT servers. Specifically, we logged the crypto operations and captured the transmitted packets during experiments. Then we computed energy consumption using energy numbers from those two institutions where they actually measured energy consumption for crypto operations and Wi-Fi packets on a smartphone and a Wi-Fi interface card. For experiments, we turned the three knobs. First, the number of session keys that can be cached for the future use, and the underlying protocol for authorization, TCP or UDP. And finally, the distribution key management to be updated using public key cryptography or to be permanent for the resource-constrained devices that cannot afford the public key cryptography. And this graph shows the result, estimated energy consumption of an IoT server connected by different numbers of clients, 16, 32, and 64 clients. And the IoT server can save energy on communication with auth by caching session keys a priori. For example, getting 64 session keys at once rather than requesting the session key every time a client connects to it. However, having more cache session keys can increase the effect of an attack in case the server with 64 cache keys gets compromised. So there's a trade-off between the energy and security guarantees. And for the underlying protocol, choosing TCP can provide reliable channel between the server and auth, while UDP can be used to save communication energy. And UDP is also a good option for resource-constrained devices which cannot afford the TCP stack. And just to remind you, the distribution key here is an encryption key to encrypt the session keys. And for such distribution keys, updating the distribution keys can limit the impact of a stolen distribution key at a cost of public key cryptography to update it. And this cost of public key cryptography is indicated as a light blue color in the graph. So for resource-constrained devices that cannot afford the public key crypto, we can choose to have the distribution key permanent. We also included TLS in this experiment as a reference. Although SST configurations use less energy than TLS in all three cases, we do not claim that SST is better than TLS because TLS has different nice security guarantees that can be useful under certain circumstances. So overall, the results show that SST can provide nice trade-offs between the security guarantees and energy consumption to support a range of heterogeneous security requirements from safety critical systems such as nuclear power plant and wireless sensor nodes. And we also have more results for the IoT clients in our CPSWA conference paper. We also undertook another set of experiments for a sender. I'm not sure whether I should go through this because of the time. Okay, I'll really quickly go through this. So we used four different settings for this experiment. And we used SSLTS as a reference, and also we used secure connection, individual secure connections between the sender and receivers, but with a shared session key among all the sender and receivers. This can save the energy for encryption because in TLS, the sender has to encrypt each message for each receiver differently, but in this case, the sender only has to do encryption just once. And in the third setting, we used a pops-up MQTT message broker who can deliver the message to the receivers on behalf of the sender so that the sender can save energy. And in the fourth setting, we used a shared key with UDP broadcast, assuming that the sender and receivers are in the same local network. So I'll quickly go through this graph. So we could provide nice trade-offs even for this one-to-many communication using those four different experimental settings. And we can, so to illustrate this, we can choose to have expected battery life less than 10 days or more than 600 days, depending on the configurations. Okay, so far I went through the evaluation of SST, and now I'd like to introduce our recent ongoing work on the defense of denial of service attacks with SST. So as shown earlier, SST can protect the Internet of Things from network-based attackers through authentication and authorization. SST can also limit the impact from compromised IoT entities through access revocation. However, there are other types of attacks that can be even more challenging to defend against, such as the denial of service attacks. One of the more challenging, the intention of the denial of service attacks is to breach the availability of the system. In other words, making it unusable as the dying server became unavailable as a result of the distributed denial of service attack. For such attacks, it might not be enough to have secure channels and encryption against the flooding network traffics from the botnet. So let us assume that the attackers want to cause a denial of service in the IoT's authorization service. If we are using a cloud-based solution for authorization, such as Amazon's AWS IoT, it is highly likely that the attackers will target the cloud computers rather than individual IoT devices to maximize the effect of the attack. Or they could also target the connection between the cloud server and the IoT devices rather than targeting the cloud itself. But if we are using SST, the attackers will target the local authorization entities auth. And thanks to the SST's architecture, the effect of auth failure will be limited to the local authorization service rather than the entire system in the IoT. For the attackers to take down the entire system, they will need to launch more organized attacks to target multiple auths at the same time, which will take more effort and prior knowledge for the attackers. So SST already has some architectural advantages to those attacks. And furthermore, we want to make SST more resilient even when some of the auths are under a denial of service attack. And in the literature, different strategies have been used to mitigate the effect of those attacks depending on where you deploy the countermeasures for those attacks. If you want to mitigate those attacks at the attack source, you will need to prevent the computers from being compromised or from turning into a botnet by deploying solutions such as malware detection systems. If you are planning to defend against those attacks while the flood of traffic is on the fly, then you will mitigate the effect by putting network filters like firewalls. However, sometimes even with these two kinds of solutions, there can be attack traffic reaching to the destination, the victim computers. So finally, we can try to mitigate the effect of at the victim's site, having the victim computers endure the attacks by maintaining as much availability as possible, even under DOS attack. And SST's defense falls under this final category. So our threat model of a DOS attack is that the attackers will likely target auth to cause denial of service in authorization services in SST and to maximize the impact of attack. And the goal is to enhance the availability of authorization service of the IoT even when some auths are under attack of denial of service. So our strategy is basically similar to those of other distributed systems, including contents distribution networks such as Akamai. And it is to replicate and distribute the authorization information throughout multiple auth to enhance the availability. So how can we resist DOS attacks using SST? I'm not sure if I would have enough time to explain it, but we'll really quickly go through it. So there should be multiple auth so that we can back up and replicate the authorization information among auth. So those rectangles are auth and those circles are the IoT devices or things. So as a preparation, this auth A1 backs up the authorization information to other trusted auth. Then the things will be able to detect this attack because they will notice that they can't be authorized by A1 anymore. Then, assuming that things can discover other auths, they can migrate to other auths and continue to use the authorization service. But how do we select from multiple possible migration plans? For example, here there are three auths, where A1 and A2 trust each other, and A1 and A3 trust each other, and T1 accesses T2. For For the case where A1 becomes unavailable, we may choose to have T1 migrate to A2 or A3. However, if we choose to have T1 migrate to A2, then it will lose the connection with T2 because there is no trust relationship between A2 and A3. So we end up choosing the plan where we migrate T1 to A3 in case of the A1's failure. So we need to consider the trust relationships between auth and access activity between things to choose the migration plan. In addition, we also need to consider the cost of things and authorization workload for better efficiency and stability of the authorization service after migration. And to find out the migration plans for better availability at a lower cost, we formulated the migration plan synthesis problem. First, we defined the requirements, the access between things and trust between auth, and pruned the plans that do not satisfy the requirements. Then, among the feasible plans meeting the requirements, we choose a plan with minimal cost using ILP solved by an ILP library in Java called OJ-Algo. And for the design and implementation of those defense in SST, we implemented the migration capability as part of SST, including a migration plan solver and backing of authorization information and actual migration. We also performed initial experiments to demonstrate the availability even under simulated DOS attacks using a network simulator NS3. Right, so now I'm moving on to the last part of my talk. To conclude, SST has the following benefits. First, the SST provides authorization for a wide range of heterogeneous IoT entities from sensor nodes to safety-critical systems. And it can enable internet-scale deployment with increasing connected devices and traffic. The software building blocks in SST also help deployment of IoT security solutions by system designers with minimal understanding of security. There can be a possible integration with other IoT-related efforts, such as securing the constrained application protocol. And SST also provides resilient authorization service even under the denial of service attacks. As future work, there are still missing pieces to be found. For further security in the IoT, we also need to be able to detect the malicious behavior of compromised IoT entities and revoke their access. And for ease of deployment, further studies need to be done the usability of SST. It's also important to study efficient ways of initial setup of SST, especially registering the IoT devices with auth. Using auth as a center for more security guarantees for the IoT can be another future research direction, such as using it as a software attestation center. And for further information, please see our GitHub repository. And before I finish, I'd like to express my gratitude to those who made this work possible. Firstly, I'd like to thank professors in my dissertation and qualifying exam committee for their advice and guidance. And I also sincerely appreciate the support from the staff of our research group and the department. And I'd like to thank the mentors and collaborators regarding my thesis work who are mostly here for their help and advice. I also appreciate the support and research inputs from the current and former colleagues and visiting scholars in the Ptolemy project team and DOP Center, including but not limited to those who are listed here. And finally, above all, thank you everyone who is here today for your presence and attention, and I'll be happy to take questions. Does anyone have questions? Oh.
In one of your analysis, security analysis of your SST, you assume that each auth is secure.
Yes.
And in your DDoS, you're like there's chances one of the auth is compromised, but that compromise is not being taken over. It's just a denial of service. Have you
Right.
thought about if a malicious user just join your network via providing his own auth, and it's secure still in the sense of being secure to himself, but in your entire model, it doesn't seem to be. It seems to be violating your previous assumption of the security.
Okay. Oh, that's actually a very interesting question to detect a new incoming auth that can be malicious, right?
Yeah.
Well, so it's like there's a problem at the very initial step of the system in that case because the incoming auth is already malicious. So one way to protect against that kind of attack is to having a robust initialization process, adding new auth. But yeah, there will be many ways to authenticate or make sure whether the incoming auth is not malicious. But I think that can be an interesting research question, although it's not considered in current work.
So is that your system need to still centralized organization to orchestrate this auths, or is auth network kind of self-maintaining?
So currently we are trying to have it self-maintained, so they can autonomously to trust others. Like in OpenPGP, the people decide to whether the trust others in the case. So I think but that will be an interesting idea to have like super auth that can coordinate multiple auths so that we can have hierarchy. So yeah, basically we're trying to have it autonomous, but yeah, the idea is to have hierarchy.
So one of the properties that intrigues me about this architecture that I don't think you really mentioned, or maybe I missed it, but is that an auth can continue to provide authentication and authorization services on a local network even if it gets completely disconnected from the internet.
Yeah, sure.
Right. And so to me, that's an essential feature in a lot of safety critical systems like factory automation or on vehicles or things like that, where connectivity is not assured. So, and even in the presence of denial of service attacks, like the DIN attack, if your edge computer has two network faces, which I think is kind of the preferred design through a network computer, right? And under the presence of an internet storm, it can still provide services on the local network, assuming it's providing some firewalling between the two. And so it seems to me that this is a very important property.
Yes, exactly. Yeah, thank you for mentioning that for me. So yeah, I should have mentioned that, but yeah, absolutely. The auth can provide like absolute protection for the internal network by disconnecting the connection through the internet. So in the case of DOS attack, we can just disconnect the internet, the one phase to the internet connection, and it can be also used when the things in the local network are compromised and start to generate attack traffic, outgoing attack traffic. Then we can provide containment by disconnecting. So it's like it can work in two ways.
Yeah, so this is in notable contrast to the Google problem last February, right? Because, I mean, in that situation, if you had one of their routers, you couldn't even talk to your local printer.
Right.
You couldn't print objects on your local. You couldn't print anything on your local network because you'd lost connectivity to the authorization server in the cloud.
Yeah. Thank you for bringing that up.
So I have a question about, one of the IoT devices you mentioned earlier was a forest fire monitor. So the hard part with that is it's not connected to the internet, presumably. It's connected very sparsely.
Right.
Like a soil sample monitor, you have your off, presumably like in your office, and you have to walk.
Yeah.
The thing. So can you proxy the security protocols, or how does that work?
Yeah, I remember we discussed this before, right? So I actually found interesting research on that kind of topic using a drone as a key distribution center. So in that case, drone is like a mobile edge device that authorizes the sparsely located wireless sensor nodes. Yeah, that'll be a very interesting direction too. Thanks. Yeah. Do you have any?
I have a quick question.
Okay.
Well, so for the denial of service, I was wondering if you looked into so there's distribution systems where if something goes offline, they automatically change where they're connecting to using like a hashing system.
Mm-hmm.
Whether you use thought about using like the keys, the last key given to a device before auth went offline as a means of just selecting a new auth.
Yeah.
Because you can do Cisco security guarantees based on that. Like
Yeah.
Everyone floods this auth, but their last key says it goes someplace else. Then either those other auths are down, or you guys are misbehaving. And you can try and figure things out based on that.
Yeah. Exactly. So to enforce that like policy or make sure that the thing doesn't migrate to some malicious auth, we have the if the thing can afford the public cryptography, the auth issues a certificate for other trusted auth that the thing will migrate to, so that the thing can verify the certificate. And also for the things who cannot afford the public cryptography, we use the notion of migration token. So it's encrypted new distribution key encrypted by the current distribution key of the thing, so that it can verify. And in that case, we also use the message authentication code key only for verifying the authenticity of the migration token. Thanks. Do you have any other questions?
All right.
Okay.
Thank Hokeun.
Thank you so much.